The chamber was sealed for millennia, undisturbed since the last human footprints faded from the lunar surface. The civilization had sent 12 explorers to the moon, 12 brave souls who planted flags, collected rocks, and took photographs, before returning home. But they had only scratched the surface, visiting a mere fraction of the lunar landscape, the side that always faced Earth. The far side, incorrectly called the dark side, despite receiving just as much sunlight as the near side, remained largely unexplored, its secrets hidden from direct human observation. The ancient chamber lay there, buried beneath the regolith of a crater in the southern hemisphere of the lunar far side, waiting to be discovered. In 2019, a small rover named Yutu-2, Jade Rabbit, deployed from China's Chang'e-4 lander, became the first to explore the far side's surface. As it traversed the ancient landscape, its instruments began detecting anomalies beneath the surface, strange readings that defied conventional explanation. What these readings revealed would forever change our understanding of not just the moon, but potentially the entire history of our solar system. The moon's far side had finally begun to reveal its secrets. Indeed, our relationship with the moon is as old as humanity itself. Ancient civilizations tracked its phases, used it to mark time, and wove it into their mythologies and religious practices. Cave paintings from over 15,000 years ago show lunar calendars, evidence that even our earliest ancestors recognized the patterns in the moon's appearance and movement. Every human culture throughout history has some connection to the moon. Stories about it, rituals timed by it, or explanations for its presence in our sky. And yet, despite this long relationship, the moon has kept many secrets from us. The most obvious of these secrets was its far side, a hemisphere that remained completely hidden from human eyes until 1959, when the Soviet spacecraft Luna 3 captured the first images. Those grainy photos revealed something surprising. The far side looked dramatically different from the familiar face we see from Earth. While the near side features large, dark regions called Maria, vast plains of ancient solidified lava, the far side is predominantly covered in craters and highlands. This stark contrast immediately presented scientists with a mystery. Why would the two hemispheres of the same celestial body look so different from each other? This dichotomy suggested that the moon had a more complex history than previously imagined. Scientists formulated various theories over the decades, but definitive answers remained elusive. The far side, without direct human exploration, kept its deeper secrets intact, and while the Apollo missions revolutionized our understanding of the moon, they all landed on the near side, leaving the far side untouched by human instruments until recently. The Chang'e-4 mission changed everything. Named after the Chinese goddess of the moon, the spacecraft touched down in the von Karman crater within the South Pole Aitken Basin on January 3, 2019. This basin is one of the largest impact structures in the solar system, spanning 2,500 kilometers in diameter and 13 kilometers deep. Scientists had long suspected it might contain material from the moon's mantle, potentially offering unprecedented insights into the moon's internal composition and formation. As Yutu-2 in 2020, CO2 began its exploration, it deployed a ground-penetrating radar system capable of scanning up to 40 meters beneath the lunar surface. The data it sent back was extraordinary, revealing layer upon layer of distinct materials like pages in an ancient book, each telling part of the moon's 4.5 billion-year history. But among these findings, something unexpected emerged. The rover detected unusual materials that didn't match the typical lunar composition. Further analysis suggested these might be remnants of something that had impacted the moon long ago. Not just another asteroid or meteorite, but something far more significant. The implications were startling. For decades, the prevailing theory about the Moon's formation was the giant impact hypothesis. The idea that a Mars-sized body called Theia collided with the early Earth around 4.5 billion years ago, with the resulting debris eventually coalescing to form the Moon. This theory elegantly explained many observations about the Moon's composition and orbit, but it had gaps. The data from Chang'e-4 and Yutu-2 offered new evidence that could help refine or even challenge this understanding. The ground-penetrating radar revealed distinct layers of material beneath the lunar surface, including what appeared to be fragments of the impactor itself, preserved for billions of years in the relatively undisturbed environment of the far side. If confirmed, this would be the first direct evidence of Theia, the protoplanet whose collision with Earth created the Moon. This remarkable preservation was only possible because the far side, shielded from Earth and its gravitational influences, experienced less volcanic activity than the near side. The near side's Maria resulted from massive lava flows that would have obscured or destroyed such evidence. But the far side remained relatively untouched, a pristine record of the early solar system. But that wasn't all the rover found. As it continued its journey across the ancient crater floor, its spectrometer detected unusual mineral compositions that didn't match anything previously seen on the Moon. Analysis suggested these minerals required formation conditions unlike anything known to have occurred on the lunar surface, perhaps extreme pressures and temperatures that could only be explained by a cataclysmic event on a scale even beyond the Moon-forming impact. Some scientists proposed a radical theory. What if the far side of the Moon wasn't just cratered differently because of volcanic activity differences, but because it had captured material from another celestial body entirely? The data indicated minerals that resembled those found in certain types of meteorites, but in concentrations never before seen. This raised the possibility that a large body, perhaps a second moon or small planetesimal, had collided with and merged into the Moon's far side long after its initial formation, creating the dichotomy we observe today. This theory, sometimes called the Big Splat, suggests that the topographical differences between the near and far sides aren't just the result of different cooling and volcanic histories, but represent a fundamental compositional difference resulting from this ancient collision. The far side's additional crust thickness, about 15 kilometers thicker than the near side, supports this idea, as does the curious asymmetry in potassium, rare earth elements, and phosphorus, collectively known as creep elements, between the two hemispheres. The radar data from Yutu-2 added weight to this hypothesis by revealing distinct boundaries between different material layers, some of which appeared to have been thrust upward and mixed together in patterns consistent with a major impact event. If true, this would mean that what we call the Moon is actually a composite object, the result of not just one, but at least two major collisions in the early solar system. This revelation forces us to reconsider the entire history of the Earth-Moon system. If the Moon experienced such dramatic events after its initial formation, our understanding of the early solar system's stability might need revision. It suggests a more chaotic, collision-rich environment than previously modeled, with implications for how we understand the evolution of all inner solar system bodies, including Earth itself. And there was more. As the rover's instruments probed deeper, they detected something that left scientists puzzled: unusual variations in the magnetic field in specific regions of the far side. The Moon doesn't currently have a global magnetic field like Earth's, but certain lunar rocks show evidence of magnetization, indicating that the Moon once had a much stronger magnetic field in its distant past. The new data suggested localized magnetic anomalies of unexpected strength and pattern, concentrated in areas with those unusual mineral compositions. This raised another fascinating possibility. What if some of these materials weren't native to our solar system at all? The early solar system was bombarded with material from various sources, including potentially interstellar objects passing through. Recent discoveries like Oumuamua and Comet Borisov have confirmed that interstellar visitors do pass through our system. In the chaotic early days of the solar system, such objects would have been even more common, and some may have impacted the Moon, leaving behind traces of their exotic compositions. The far side, with its relatively undisturbed surface, would be the perfect preservational environment for such material. Protected from Earth's influences and with minimal geological activity compared to the near side, it could contain chemical and isotopic signatures unlike anything in our native solar system. If confirmed, this would represent the first identified preserved material from beyond our solar system, a truly remarkable scientific treasure. As exciting as these discoveries are, perhaps the most significant finding came from Yutu-2's spectrometer when it detected clear evidence of water molecules bound within certain minerals in the lunar soil. While previous missions had detected water ice in permanently shadowed craters near the lunar poles, this finding was different. It suggested water integrated into the mineral structure, preserved in areas that regularly experience the extreme heat of the lunar day. The presence of this water carried profound implications. Its chemical signature was distinct from what would be expected if it originated from solar wind interactions with the lunar surface, the prevailing explanation for most lunar water. Instead, it appeared to be primordial, dating back to the Moon's formation. This suggests that the Moon may have been wetter at its birth than previously thought, contradicting older models that proposed a completely dry formation. But how could water survive the cataclysmic heat of the Moon-forming impact? Some scientists propose that it arrived later, delivered by the same secondary impacts that created the far side's unique composition. Others suggest that water molecules could have been trapped deep within mineral structures during the Moon's formation, protected from the heat, and preserved for billions of years. The distribution pattern of this water provides additional clues. It appears more concentrated in regions with those unusual mineral compositions, suggesting a potential connection between the water and the proposed secondary impact event. If water-rich bodies struck the Moon after its initial formation, they could have delivered both exotic minerals and significant quantities of water that were then preserved in the relatively undisturbed environment of the far side. This discovery has immediate practical implications for future lunar exploration and potential colonization. Water is perhaps the most valuable resource for space exploration. It can be split into hydrogen and oxygen for fuel and air, and of course, it's essential for human survival. If substantial quantities of accessible water exist beyond the permanently shadowed craters, it could dramatically reduce the cost and complexity of establishing a long-term human presence on the Moon. The water findings also connect to another mystery that has long puzzled lunar scientists: the presence of rust on the Moon. In 2020, data from the Chandrayaan-1 mission revealed hematite, an iron oxide that typically requires both oxygen and water to form, at several locations on the lunar surface, including near the poles and, surprisingly, on the far side. Without a substantial atmosphere or liquid water, the Moon should be a rust-free environment. Yet there it was, iron oxide, its signature unmistakable in the spectroscopic data. The discovery of bound water in minerals provides a potential explanation. If water molecules can be freed from these minerals through micrometeorite impacts or temperature changes, they could interact with iron in the lunar soil. Combined with oxygen from Earth's magnetosphere, which extends far enough to reach the Moon during certain parts of its orbit, these elements could produce the rusting effect observed. The concentration of rust on the far side particularly in areas with those unusual mineral compositions, suggests a connection to the exotic materials detected by Yutu-2. The lunar far side's secrets extend beyond geology and chemistry. As the rover continued its exploration, it deployed sensitive instruments designed to take advantage of the far side's unique position as the most radio-quiet environment in Earth's vicinity. Shielded from terrestrial radio emissions by the entire mass of the Moon, the far side offers an unprecedented opportunity to detect faint radio signals from the distant universe, including potentially the earliest stars and galaxies that formed after the Big Bang. While Yutu-2's instruments were primarily designed for lunar studies, they included radio detection capabilities that have provided tantalizing glimpses of what might be possible with more specialized equipment. Future missions planned for the lunar far side include radio telescopes specifically designed to exploit this radio-quiet environment, potentially opening a new window into the universe's earliest epochs. As astronomers anticipate these future observations, they've begun to realize that the lunar far side might hold more than just material secrets. Its position could make it humanity's most valuable astronomical observation point, a unique vantage that could reveal aspects of the universe impossible to see from Earth or even from space telescopes affected by Earth's radio noise. In this sense, the far side might be considered a cosmic gift, a natural platform for peering deeper into space and time than ever before. The implications of these discoveries continue to ripple through the scientific community. If the Moon is indeed a composite object, formed through multiple major impacts and preserving material from different sources within our solar system, and potentially beyond, it represents an unprecedented scientific archive. Each layer of the lunar far side contains information about a different chapter in the history of our corner of the galaxy, preserved more perfectly than anywhere else in the inner solar system. This perspective transforms how we view the Moon, no longer just Earth's pale companion or even a potential stepping stone to Mars. The Moon becomes a scientific treasure of almost incalculable value. Its far side, in particular, represents a unique laboratory containing evidence that could answer fundamental questions about the formation of our solar system, the early Earth, and even the ingredients for life. The theory that life on Earth might have origins connected to lunar formation events gains new dimensions with these discoveries. If water and complex organic compounds were part of the materials delivered to the Earth-Moon system during these ancient impacts, they could have played a crucial role in creating the conditions necessary for life on Earth. The Moon, and particularly its far side, might hold the evidence needed to test such theories. As Yutu-2 continued its journey across the crater floor, each new reading added detail to this emerging picture. The rover's cameras captured images of unusual rock formations that differed significantly from those seen during Apollo missions to the near side. Some showed distinct layering patterns suggestive of sequential deposition events rather than the homogeneous composition expected from cooling lava or simple impact debris. Analysis of these formations supported the hypothesis of multiple major events contributing to the Moon's current state. The layering appeared consistent, with material being added to the lunar surface at different times and from different sources, rather than all originating from a single event like the proposed Theia impact. Each layer told part of the story, from the initial formation to subsequent bombardment to the more recent micrometeorite weathering that continues today. The most surprising aspect of these layered formations was evidence suggesting some had been formed not through impacts from above, but through upwelling from below. This indicated that whatever struck the far side had enough energy to penetrate deep into the lunar crust, perhaps even reaching the mantle, before its material was incorporated and eventually pushed back to the surface through subsequent geological processes. This evidence of material exchange between the lunar interior and surface adds a new dimension to our understanding of the moon's evolution. Rather than a simple dead world frozen in time after its initial formation, the moon, at least the far side, appears to have experienced more complex geological processes than previously recognized. These processes may have continued for hundreds of millions of years after the moon's initial formation, driven by the energy and material introduced by the proposed secondary impact. The discovery also connects to a puzzle that has long intrigued lunar scientists. Why did the moon's magnetic field last so much longer than expected? Based on its size, the moon should have cooled relatively quickly after formation, with any magnetic dynamo in its core shutting down within the first billion years. Yet evidence from Apollo samples suggests the lunar magnetic field persisted for nearly 2 billion years, far longer than models predicted. The energy introduced by a major secondary impact could explain this discrepancy. If a significant body struck the far side after the moon's initial formation, it would have delivered enormous kinetic energy, much of which would have been converted to heat. This heat injection into the lunar interior could have helped sustain convection in the core for much longer than would otherwise have been possible, extending the lifetime of the lunar magnetic dynamo. As scientists continue to analyze the data from Yutu-2 and plan future missions to the lunar far side, a new picture of the moon is emerging. One far more complex and dynamic than the simple gray satellite we've observed since our earliest days. The moon, it seems, has been shaped not just by its initial formation, but by a series of dramatic events that have left their mark primarily on its hidden face, the side that, until recently, had kept its secrets in the dark. This evolving understanding has immediate implications for planned human return to the moon. Future missions, including NASA's Artemis program and various international efforts, are already adjusting their scientific priorities to investigate these new findings. Several proposed missions specifically target the far side, with instruments designed to analyze its unique composition and structure in unprecedented detail. Beyond the scientific implications, these discoveries remind us of something profound. Even our closest celestial neighbor, the object humans have stared at with wonder for thousands of years, can still surprise us. The universe, even in our cosmic backyard, contains more mysteries than we've imagined. The moon's far side, hidden from human eyes throughout our species' existence until the space age, has patiently held its secrets. Not dark secrets, but illuminating ones that may fundamentally change our understanding of our place in the solar system. And so, as we prepare to return to the moon in the coming years, this time with the ability to explore both its familiar face and its long-hidden far side, we stand on the threshold of discoveries that could rewrite the textbooks. Once again, the chamber sealed for millennia has finally been opened, and its contents are more astonishing than anyone could have predicted. The moon's far side has begun to speak, and what it tells us may change our understanding not just of our nearest neighbor, but of our own origins on the pale blue dot the moon has circled for billions of years. Indeed, the greatest secret the moon's far side may have revealed is not any single discovery, but a broader truth. The solar system's history is written in layers, preserved in different ways on different worlds. Earth, with its active geology and weather, has erased much of its earliest history. But the moon, particularly its far side, has preserved that record in remarkable fidelity. By reading this record, we gain insight not just into the moon, but into the Earth itself, the planet that gave birth to both the moon and, billions of years later, to the curious species that would return to unlock its secrets.